The organizers asked me to do the talk in English. I'm going to switch in English for the rest of the talk. I hope it's fine for most of you. I'm going to go through two different main systems, which are batteries and supercapacitors. So the topic today will be to try to describe as much as possible, again, the state of the art and the next challenges batteries and supercaps are facing. So first of all, you have here what we call a Ragone plot, which shows the specific power versus specific energy for different electrochemical energy storage devices. So this is more or less here the power capability. If you make a parallel between this Ragone plot and the vehicle, this is acceleration, and this is the range for pure electric drive. So here, on one side of the Ragone plot, you have capacitors, which are mainly power devices with very small energy densities devices and time constant of 1 millisecond. Very high power, no energy. On the other hand, you have here batteries, high specific energy, up to 250 watt-hour per kilogram for lithium-ion batteries, and medium or low specific power. Batteries, again, are for long-time power delivery at low current, so no real huge power. And to bridge the gap between capacitors and batteries, you have here supercapacitors, which are high power devices, 20, 30 kilowatt per kilogram. Medium energy means 5 watt-hour per kilogram, 40 times less than batteries, from lithium-ion batteries. And this defines a time constant of about 5 seconds. And just to show you here a comparison with a thermal engine combustion, you have a factor of 15 between the batteries and the energy density of batteries and energy density of gasoline. So here you have more or less on the Ragone plot the position of a thermal engine. Okay, I'm going to start the topic by batteries. We'll start with very basic things about batteries, switching to lithium-ion batteries and perspectives, and then I will move to supercaps, and I will give a few words about the French network on batteries we are co-animating with Jean-Marie Tarascon. So a very basic principle on batteries. What is a battery? You have here a very schematic of a battery. You have one electrode here, a negative electrode, positive electrode, and electrons are exchanged between the negative electrode. Electrons leaves the negative electrode and goes to the positive, powering your device. At each electrode, you have what we call an active material. An active material is the material which is going to be able to exchange electrons through the load. At the positive electrode, during the discharge, you have a reduction reaction, which is a chemical reaction, which is consumption of electron, which is thus an electrochemical reaction. And this electrochemical reaction, this reduction, is achieved at constant potential, E+, which is a thermodynamic data. And then you can associate to this redox reaction a capacity. The capacity is the number of Faradays, the number of electron exchange per mole of oxidant. So you can define here milliampere hour per gram, which is, again, the number of charge a material can deliver divided by the number of electrons, the number of electrons you can exchange with it. You have the same at the negative electrode. At the negative electrode, you have positive, negative electrode, you have an oxidation reaction. So you release electrons. Electrons here are then consumed to the positive. And you define a negative electrode potential and a capacity of a material in milliampere hour per gram. And how does it work? When you discharge a battery, this is a voltage versus time or versus number of lithium. Anyway, it's not a big deal. So this is a constant current discharge, voltage versus time. You discharge the battery at a constant potential, which is a cell voltage difference between positive and negative. And then when you recharge, you do the opposite. So the capacity of a battery multiplied by here the cell voltage gives you the energy density. Okay? And rechargeable cells are called accumulators, and now everybody uses the word batteries for rechargeable cells. So basically, batteries, key materials, the active material at the positive electrode, which defines the specific capacity, the potential, the cell voltage, and then the energy. So now let's move to lithium-ion batteries. Lithium-ion batteries are the most breaking through discovery of the 20th century in terms of batteries. So it's about 3 to 6 times the energy density of a lead-acid battery. How does it work? At the negative electrode, you have graphite, a graphite anode. So you can view a graphite anode now as a stacking of graphene layers, which is more sexy. So you have graphene layers here, and in between the layers, this is carbon, okay? in between the layers, you are going to intercalate lithium ions. For instance, here, you have 6 carbon here, carbon ring, plus 1 lithium, plus an ion, plus 1 electron, is going to give this compound LiC6. But here, in this material, lithium is lithium ion. Okay, this is not lithium metal. This is a carbon which is going to have to see a decrease of oxidation state. So this is what we call the lithium ion intercalated graphite, and this is where does the lithium ion battery name come from. So this redox reaction, so intercalation of lithium ion into the graphite here, is achieved at very low voltage versus lithium, 0.5, and gives a capacity of 362 milliampere per gram. So this is today the negative electrode that you have in your cell phones, in your laptops, whatever you want. At the positive electrode, this is a lithiated cobalt oxide, which is the beginning of a lithium-ion battery. It's a lithium cobalt oxide, and during, for instance, the charge of a discharge, you are going to exchange lithium plus ions. So during the charge, here, you are going to remove lithium plus ions from the CO2 structure, and these lithium plus ions are going to be intercalated into a graphite electrode. And then here you discharge and then you charge. You can exchange 0.5 lithium for 1 LiCO2. So this defines a capacity of 177 milliampere per gram, and the cell voltage is the difference between the positive electrode and negative electrode. Something is missing here, is about 4.2 volt versus lithium. So the cell voltage of a lithium-ion battery is 3.7 volt. And the capacity is 60 ampere hour per kilogram, energy around 200 watt hour per kilogram. But when we talk about lithium-ion batteries, it's a big, big, big family. You see, all of these are lithium cells, and lithium-ion batteries that can be rechargeable are just here on this left corner. So I'm going to go into a bit into the details of current state-of-the-art of lithium-ion batteries. There is no one lithium-ion batteries. You have several lithium-ion batteries depending on the chemistry. The chemistry of a cathode defines the name of a battery. Okay? So we're going to see 3 different kinds of materials: 2D materials, 1D materials, and 3D spinel structures. So historically speaking, the first material which was used for lithium-ion battery is the lithium cobalt oxide. What is a lithium cobalt oxide? It's a stacking of CO6 octahedras stacked over the C-axis, and in between these layers, here, this is called the 2D structure, two-dimensional structure. You have lithium plus ions, and during, for instance, the charge, you are going to remove the lithium plus from the intergap distance and exchange electrons. So this is this reaction. You oxidize lithium CO2 into lithium 1 minus 6 CO2 plus X lithium plus 6 electrons. And this is what happens. You have a cell voltage versus the time at constant current or the capacity. And when you discharge, when you remove the lithium ions here, you end up to a point here at 4.7 volt. But what is very important to understand is that as long as you remove lithium ions more than 140 milliampere per gram here, this is irreversible. What does it mean? It means that when you have removed more than 0.5 lithium, the structure of LiCO2 changes, and then you cannot recover the structure. So you are limited in capacity to 0.5 lithium. This is the first drawback of lithium cobalt oxide. But the key here is the thermal issue. When you are going to heat LiCO2 oxide beyond 170 Celsius degrees, you are going to have a break of the cobalt oxygen bond, and this breaking is going to release a lot of heat. And this is called the thermal runaway of a battery. It means as long as you go beyond 160 Celsius degrees, the battery goes into thermal runaway. It means that the cell temperature can reach 800 Celsius degrees, and you cannot extinguish the fire. This is what is called the lithium fire. It was one of the problems of Dreamliner. In fact, it was the problem of the Dreamliner. So people since 15 years have tried to tackle the issue of safety. And to make a long story short, they end up with, they try to replace cobalt, because the cobalt problem comes from cobalt oxygen bound. They try to replace cobalt with other active materials. And they end up with a solution of what is called, they replace 2/3 of cobalt with 1/3 of manganese, 1/3 of nickel. And this nickel is nickel 2, means that it can be oxidized into nickel 2, nickel 3, nickel 4. This manganese is +4, is not active at all. So it means that you replace a part of a cobalt with one inactive material, but with another active material which can be oxidized, so that in fact you don't lose a lot of capacity, but you have something which is, thermally speaking, much more stable. So today, most of your laptops are using NMC. NMC stands for nickel manganese cobalt cathode. So this is the cathode which is used. And you have also what is called NCA, nickel cobalt aluminum doped, but more or less all of this is lithium cobalt oxide based systems. Second type of cathode is what we call LFP, lithium iron phosphate. This is just LiFePO4, which is a mineral. You can find it in soil, iron phosphate. And you have an intercalation reaction of lithium plus into FePO4. So this is really interesting because it's a second type of chemistry. Why? It's completely different. Because first, there is no thermal runaway. There is no more cobalt-oxygen bonds. Second, there is a very flat, constant voltage discharge plateau at 3.5 volt. And this is here the cell of a LFP battery versus capacity or time. And you can see the discharge is a very flat voltage plateau. So this structure is very open, so that you have high power because the lithium plus ions can migrate very fast inside this electrode. It can be recharged quite fast. The thermal stability is good, but 3 main drawbacks. First, you lose about 300 millivolts as a medium cell voltage, so that the energy density is about 30% less or even more than lithium-ion batteries based on NMC materials, only 120 watt-hour per kilogram. Second, when you heat the system, iron here is partially soluble, so at high temperature, these batteries are not really good. And the third one is that LFP is very insulating material, electrically insulating, so that you need to make what we call a carbon coating here, 2 nanometers of carbon coating to make it conductive. That's another drawback. But really, LFP batteries are lower voltage, lower energy density, fast recharge rate. And the third one, which is a technology from Nissan and Renault, is based on lithium manganese oxide, LiMn2O4. It's also an intercalation reaction of lithium plus into Mn2O4. You see that the cell voltage, 4.2 volt, is a bit higher. This is the discharge and the charge. And for sure, the main advantage of LMO is the low cost, higher cell voltage, higher power, because this is a very 3D open structure where lithium can diffuse fast into the materials. But here again, you have minus 20% of capacity versus NMC. You are limited to 100 milliampere per gram. And when you have the temperature that reaches 55 Celsius degrees, you start to have a manganese dissolution by dismutation. So this is a problem. You have to manage the heat of a battery. And now, so it was state of the art. And what about advanced lithium-ion batteries? So all these intercalation reactions we have described, you have a limitation in capacity to 370 milliampere per gram for carbon, for instance. The idea will be to move to higher capacitive anodes. So for the anodic side, what you can try to do is to use what we call lithium alloying reactions, which are 30 years old reactions, very well known. And you take, for instance, a metal, and plus is missing here, sorry, I apologize for that. And when you polarize this metal, you can reduce lithium plus into the metal to form the lithium alloy. And you can put up to 4.4 lithium per metal. So that it means that now, if you have a look to the specific capacity of a metal, if you take carbon, 1 lithium, 1 Faraday for 6 carbons, means 372 milliampere per gram. And you can see here, silicium, theoretically can reach 4,000 milliampere per gram, 12 times more. Why? Just because you can do the silicon plus 4.5 lithium plus 4.5 electrons is Li 4.4 Si. And this is a outstanding capacitive anode. Just small problem. You can see here, metal alloy, 400% volume expansion when you do the lithium alloying reaction. So you charge the battery, you discharge the battery. You charge the battery, you discharge the battery. You do 3 cycles. Mechanically speaking, these materials are not stable at all. And this explains you why, by this day, there is a huge, huge, huge research effort on silicon. Panasonic has launched this new silicon generation battery, but it's very tricky to solve. How to solve it? This is an example taken from the literature. The idea is to try to use nanostructured silicon anodes. Why? Just because, in fact, silicium anode. Just because, in fact, if you use nanostructured materials, you can have voids, volume, to buffer the mechanical expansion between the particles. And you have here a strategy. You start from porous carbon. You do a CVD of silicon onto it, or silicium onto it, sorry. And then here you have this 10-micron particle decorated with silicium. You have here, this is amorphous silicium, and this is a graphite, here, TEM image, graphite layers. You can see that this is graphite, 0.33 nanometer between the graphene layers. And you have here, more or less, 15 nanometers size silicon particle. Have a look. Cyclability is very good. Capacity, 1600 milliampere per gram. You limit the number of lithium intercalated alloyed lithium by 2.5, no more. And then you have something very stable. So this is an example of how to make a silicon-based anode. You have plenty of other strategies like ink formulation, and the commercialization, I would say, is in progress. But this is a very, very hot topic. Another key advance, which is very recent, is not yet under commercial. This is discovery in 2007 by Mike Thackeray in US of what we call lithium-rich phase. NMC material, remember, you have CO6 layers and lithium plus in betweens, okay? When you have NMC material, means that the site for cobalt is shared between cobalt, manganese, and nickel. So you may have one transition metal in this site, okay? Lithium-rich phase are here on the site of a transition metal, you put a lithium plus, and then you have a lithium, additional lithium in the structure. Okay, so that's a way to increase the capacity. But people who did that in 2007, they did not understood how did it work. And if you take this structure, this is in fact nickel 2, manganese 4, cobalt 3. Nickel 2 can be oxidized up to nickel plus 4. This one is maximum. This one can be oxidized up to plus 4. So you can theoretically exchange 0.4 electrons for one molecule. And if you do a cycling with this material, you can see that on discharge, this is the potential versus time at constant current, you can exchange up to 0.9 electrons. So there's a problem. Twice more capacity than the theoretical, based only on the oxidation state of metals. Why? This has been solved very recently by Jean-Marie Tarascon. You have here the cell voltage versus time or capacity, whatever you want, during charge. It's for a ruthenium-based material, okay? And what you see is the first plateau is oxidation of ruthenium into ruthenium plus 5. Okay, you replace cobalt by ruthenium. And here the second plateau is oxidation of oxygen into peroxospacey. And this is completely a new paradigm change because it shows that you can have first a cumulative evidence of redox reaction on the metal and also a redox reaction on the oxygen. It was the first time that it was understood last year. And now it opens the way, it paves the way for new active materials for positive electrode of lithium-ion batteries with higher capacity based on the redox, not only on the metal, but also on the oxygen group. And this is fundamentally new. And you can have a look back to materials which were previously disregarded, like niobium oxide, whatever you want. So this is really interesting. When this is really ongoing, it's 18 months old. What technology for the future? Because we did more or less current state of the art, advanced lithium-ion batteries. What for 10 years? Oh, sorry. If you take the periodic table, you have lithium, which is very nice anode, low potential, lightweight, and oxygen, high potential, low weight, 2 Faradays. So you can combine and assembling a lithium-air battery. What is lithium-air battery? Very interesting. This is at the negative electrode, you oxidize lithium into lithium plus. At the positive electrode, you reduce oxygen into O2 minus, peroxide. Okay? Theoretically, 2.3 kilowatt hour per kilogram. 5 times lithium-ion battery. If you put this in electrical vehicle, means a 1,000, 1,500, 500 kilometers autonomy. Realistically, 1 kilowatt hour, 800 kilometer autonomy for electric car powered by lithium air. Very, very nice. 4 volt, outstanding. But, problem. First problem. When you charge the cell here, you go up to 4 volt. When you discharge the cell, you go down to 2.5 volt. There is a huge difference in the cell voltage because there are a lot of resistances. It's very complicated. Second problem, when you discharge the cell here, when you reduce the oxygen, you don't go directly to the peroxospace. You go through this intermediate, which is superoxide ion. Superoxide is the species which is responsible for the aging of a human body. This is a superoxidizing agent. So as long as you form superoxide, you are going to oxidize the electrolyte, you are going to oxidize the carbon, you are going to oxidize everything. So the key problem to solve for lithium-air battery is to trap this superoxide species, which is a reaction intermediate formed during the discharge. So as a result, there are several issues that have to be tackled to try to make a lithium-air battery working. Instability of lithium metal, because this is a negative electrode of lithium, versus electrolyte and polarization. Low kinetics for reaction. Precipitation of Li2O2. So this is an insulator. What is it? Yeah, this is an insulator. So it's not really good. And cycle life is very poor because of a superoxide. However, last week, so it was October 30th, 2015 in Science, the group from Claire Gray at Cambridge University in UK, they have published a very interesting paper. It does not solve everything, but this is the beginning of the answer. So they put, okay, what did they found? You remember what I show you here. This is the discharge and this is the charge, huge polarization. You see, they use graphene oxide as an active material, and this is the discharge, and this is the charge. Polarization is only 0.2 volt. So they have solved a part of the problem. How did they do? Well, just a bit science. So they just used a redox mediator, iodine. And this iodine here, during the charge, you are going to form I3-, and this I3- is going then to oxidize LiOH into water. Then you remove all the polarization, let's say. But this is a very interesting concept and a tricky idea that can be very interesting for the future of lithium, but this does not solve the appearance of the superoxide ion. So it solves a part of the problem, but this is not the solution. But this is very interesting. Next perspective, sodium versus lithium. There are lithium-ion batteries. Why not sodium-ion? Same materials, intercalation, alkaline, same process. Sodium carbonate is much less expensive than lithium. Abundance, 10 to 5 more sodium than lithium. 2 drawbacks. First, the potential of sodium, 300 millivolt lower. Means that in fact, a sodium-ion battery will discharge 300 millivolt lower than lithium-ion. You will lose 25% of energy. Second drawback, the capacity. You have 1/3 of capacity because sodium is heavier than lithium. Sodium is 21 grams per mole, lithium is 7. So you lose 1/3 of 2/3 of the capacity. Never mind. This is a very interesting alternative to lithium-ion batteries at lower cost. Of course, you know you are going to lose energy, but this can be very interesting for mass storage. So I will come back on this point later on. A last perspective. This is here specific energy versus different technologies, and this is to power this Nissan Leaf vehicle. So today, with the current lithium-ion technology, a Leaf can have autonomy of 160 kilometers. If you move to a future lithium-ion technology, this is what I show you with, for instance, silicon as anode and lithium-rich cathode. You can think about reaching 250 kilometers. Okay, future lithium ions. If you move to lithium air, okay, fine, more than 600 kilometers autonomy, but lithium air is really tricky. Then lithium sulfur sounds really interesting. 450, 500 kilometers. How does it work? You take lithium metal as anode and sulfur. Here, sulfur as cathode. So reduce sulfur into sulfides. And then you end up with this reaction. You form Li2S. OCV is 2.4 volt, quite low, but it's very huge capacity, so that energy density is very large. And here the sulfur is not solid sulfur, it's a sulfur which is trapped into porous carbon. And you have here a discharge plot and a charge plot. That's the theory, because practically speaking, you go through, to move from this to this, you go through all these reaction steps. And you have 5 different steps, and you have 5 different problems to solve. Why? Because you form species here, sulfides, you see here. Some of the sulfides are soluble, some of the sulfides are insoluble, insulators, and then you have a lot of problems to tackle and to deal with. However, one solution to try to solve the issue is to, again, to confine the sulfur into porous carbon, which has been done 2 years ago by a Canadian group in McGill University. These are very good results. And lithium sulfur battery starts to work today. But more, there is a recent paper here in 2014 that shows that if you take titanate material, you put sulfide, lithium sulfide on top of it, just by polarity, you can really stack the lithium sulfur onto the titanium. And then you can block and trap the sulfur onto this kind of materials. And you have a look here, this is a cycle number, 100 cycles at 1000 milliampere per gram, which is quite outstanding for lithium sulfur. And this is one way to solve the cyclability of issue of lithium sulfur. And really, lithium sulfur is very old-fashioned technology, 50 years old, but today, major advances have been done, and really, we are very close to a commercialization of lithium sulfur. To my opinion, this is the next battery that will come into the market. And just a message, my opinion again, well ahead before lithium air systems. Also, there are breaking news that you can see sometimes in newspapers, in Le Monde journals, in internet, from very serious universities, very outstanding work, maybe a bit oversold. And this is an example of last April, ultra-fast rechargeable aluminum ion battery. Why is it very appealing and sexy, the title? Lithium plus, 1 electron for 1 lithium. Aluminum, 3 plus, 3 electrons for 1 aluminum. So you can multiply by 3 the capacity and then the energy density. So this guy from Stanford University, they said that they succeeded in preparing battery based on the intercalation of aluminum ion. No one was able to make intercalation of aluminum ion, which is very tricky. However, if you have a look back to a detail of a work, first they use complex aluminum ions. You see there is only 1 minus charge. There is only 1 charge per aluminum, not 3, only 1. So their interest is a bit decreased. And then they use as well a negative electrode, which is aluminum foil, and carbon foam as a positive electrode to put the materials. So huge void volume, so volumetric energy density, very low. And then they use ionic liquids, they use different systems. Well, it's promising, definitely. It's interesting concept. But today, if you compare this performance with a lithium-ion battery, this is 10 times lower energy density for this battery. So this is just a kind of overselling, maybe I would say, of a work by very efficient communication business office from Stanford. But it's interesting, there is something, but this is definitely not the end of a lithium-ion battery. And last, there was also 18 months ago an announcement from Envia Technology, 400 watt-hour per kilogram, world record sale of lithium-ion battery. 400 watt-hour per kilogram, terrific. I mean, it's more than 2 times or 2 times the energy density of lithium-ion batteries. What's the trick? In fact, there is no trick. They use silicon-based anode. Fine, this is something which is in many labs. And also, they use pouch cells, no aluminum case. So the kg, the weight of the packaging is very light. And second, they use very thick electrodes, millimeter thick electrodes, so that you have in the same volume a lot of active material. But since you use thick electrodes, the power capability is very low. So this plot was certainly obtained at C by 10, C by 20, C by 50 discharge, at very low rate. There is no power inside, so there is no miracle. Okay, so I will move to the second part of the talk, which is about supercaps. Just have a look to what the time. Is okay? Okay, supercapacitors. Again, basic principles. I will send a bit more on applications because maybe supercaps are less known than batteries. And I will give you also a few words about microporous carbons. So same Ragone plot, you remember, capacitors, batteries. We are going to focus on here what is in between the batteries and capacitors. So supercaps, very high power, much higher power than batteries, lower energy density. High energy density, medium energy density, high power, low power. So if you make a ratio between energy and power, you have defined the definition of a time constant which is about 10 seconds. 10 seconds here means that supercaps are used. The key application of supercaps is to deliver power during 10 seconds, 10, 50 seconds. And the interest of supercapacitors, unlike lithium-ion batteries, is that you can discharge as fast as you charge the supercap. The message is that they are complementary devices. Supercaps for power, battery for energy. Supercaps, more or less, this is Usain Bolt. This is a sprinter, 100 meters. And batteries are Haile Gebrselassie, used to be the world record in a marathon race. So this is really a good example. So what's the trick for supercaps? How does the charge is stored? In fact, there is no redox reactions. Supercaps, they store the charge only by pure electrostatic mechanism. When you polarize, this is an electrode that you put into sodium chloride, seawater. If you polarize your electrode, platinum electrode, if you inject negative charges, then what you are going to see is sodium ions who are going to migrate to your electrode and balance the charge created onto the metal surface. So you polarize negatively your electrode by a charger, and sodium ions balance the charge. And you form here a capacitor. Okay? The capacitance is the product of a dielectric constant of electrolyte, because there is no vacuum, this is electrolyte here, multiplied by the surface of the electrode, divided by D, or delta, which is the approaching distance of the ions to the electrode surface. D, delta, is about few Armstrong. So this is why we can end up with 10 to 20 microfarad per square centimeter. You are going to say, 20 microfarad per square centimeter, who cares? Who cares? You're right, if you use geometric current collectors. But if you are able to use highly divided materials, like porous carbons, you take carbon, you dig holes into the carbon, and then you polarize the carbon. And at the end, if you take into account the whole surface of a porous carbon, you can reach 1,500 square meter per gram, 2,000 square meter per gram. So it means that if you just do a basic multiplication, you can store in such very porous carbons more than 100 farads per gram of carbon, which is outstanding. But there is a price to pay, which is the cell voltage. In a pure dielectric, cell voltage is limited by the electric breakdown of a dielectric, voltage breakdown of a dielectric. Here, this is the same. It's limited by the electrochemical decomposition window, electrical voltage window stability of the electrolyte. In water, you know that if you polarize beyond 1.2 volt, water is going to be oxidized into oxygen, reduced into hydrogen. If you replace water with organic solvent, propylene carbonate, acetonitrile, then you can reach 2.5 volts for a single cell, and within 0 up to 2.5 volt, you just charge the charge in supercaps by ion adsorption onto the carbon. Okay? So as a result, this is surface storage. The charge is very fast, is easily available. However, in batteries, the charge was stored inside the chemical bonds. You reduce oxidized metals, okay? So that there is much less charge in supercaps, but very fastly available, so very high power. Since this is not, there is no charge into the bulk of a material, since this is only surface storage, you can charge and discharge at the same rate, very fast. This is also something very important. When you have battery, at the charge state, you have an you have, for instance, I don't know, an oxidant. When you discharge a battery, you reduce the oxidant into reductant, okay? So it means that at the charge and discharge, both electrodes, they change the composition. Lead oxide, lead, for instance, for a lead acid battery. So it means that you have always a volume change between the charge state and the discharge state. It means that any battery will have a limited cycle life because of mechanical stress. Then this can be degraded by parasitic electrochemical reactions, whatever you want. But the basic principle of a battery is that the cycle life is limited by the volume change. Supercap, surface storage, no volume change. Theoretically, cycle life is infinite. Practically speaking, is more than 5 million cycles. So there is completely different from batteries. Okay, so I will give a few words about applications. The first application was in A380. This is for door emergency opening. So in each of the 16 doors, you have this supercap model, which is there. And obviously, this is for emergency opening, so it did not work yet. But it was a demonstration that supercaps were really safe to be implemented in this jumbo jet. So it was a niche market, the real demonstration that supercaps could do the job and safely. So then, supercaps, you can use supercaps for energy recovery. This is a tram you have in Paris, T3 line, and this is a collaboration between Alstom and Blue Solution from Bolloré. And you have on the top of a roof, you have here supercaps models, and they are used to recover braking energy of another tram which is braking on the same line. And they can be also used for pure electric drive for 100 meters to cross crossings. And this is now in many European capitals like Madrid, you have in Berlin, you have also in many towns, in Barcelona, you have in, well, I don't remember, you have 20 cities in Europe who are using this tram powered by supercaps. So this was mainly for energy recovery because of a fast recharge of supercaps. And then, which is the key application, hybrid electric vehicles. You have here the size, you know that a hybrid electric vehicle is you combine thermal engine to electrical engine. And depending on the size of the electric engine, you are micro-hybrid, mild hybrid, or full hybrid. Micro-hybrid is a very small engine, means that you do only a few key features, for example, stop and start, and braking recovery, energy recovery. And you can see these two applications is about 6 kilowatt, 1 to 2 watt hour. Perfect for supercaps. And that's the reason why, since 2012, for Citroën, they equipped all vehicles, starter alternators with supercaps. So in fact, you remove or you suppress to the batteries all the power, all the peak power delivery, which saves the lives of a battery. And also Mazda is doing that, Peugeot did that with other technique, and Cadillac is doing this, Volkswagen is going into the field, and blah. Well, this is a very nice example for supercaps. And another example, which is, I would say, is a bit at the border of what supercap can do. This is still a Bolloré. This is what they call a blue tram. In fact, it's a bus. And, and you have here supercaps on the top of on the roof of a bus. Why there is no lithium-ion battery? This is a pure supercap. This is a pure electric drive by supercap. Why? Just because you have only 1.5 kilometer autonomy. And in fact, it means that you have a very closed loop and you have stops each 1 kilometer. And this bus can transport passengers between two stops. At the stop, during the passenger exchange, they recharge the supercap in 60 seconds, 1 minute, or even more. So they take benefit from the very fast recharge and the infinite cycle life. And this is something that they are doing. And if you take into account the cyclability, the cost, which is about 10 times more than lithium-ion battery, is going to be reduced very easily. And then this, the plant opened last February, and they are producing 50 blue trams a year. Okay, now let's move to the carbon, which is the key part of the material of supercaps. I told you it was porous carbon. What do? You go, you start from a coconut shell, which is a green precursor. And then you do a first carbonization, and you end up with particles of about 5 to 10 micron. And then you do what we call activation treatment. What is an activation treatment? It's a controlled oxidation of carbon into CO2. And then you end up with pores here. And at the end, you have this particle of about 10 micron diameter. And you have a porous network inside this particle. And you create big pores, macropores, bigger than 50 nanometers, medium-sized pores, which are called mesopores, between 2 and 50 nanometers, and the smallest pores, which are responsible for the high surface area, are called micropores. They are nano-sized, but they call it micropores. And then the specific surface area can be up to 2,000, 2,015, 3,000 square meter per gram. However, so this is a real, more or less, it's from a model, it's not a real, but this is what we imagine could be a real structure of a porous carbon. However, it's very difficult to control this process, activation. It's very difficult to control the pore size of the carbon you are producing. So this is a porous volume versus a pore width, pore size, in Armstrong. So you can see this is a very narrow pore size carbon, and you can see that the pore size goes between, I would say, 0.5 to 4 nanometer, which is very large, in fact. And there was no idea, there was no way, since 10 years, there was no way to try to find a way to prepare carbons with very narrow pore size distribution. And we end up with a method, I'm not going into detail about that, but with a colleague, we were able to produce carbons with a control pore size below 1 nanometer. And what we have found here, we have found with our materials, this is a carbon pore size, this is the normalized capacitance of carbons. This is what was available at that time in the literature, okay? Between 2 and 5 nanometers with activated carbons. In fact, people were thinking that you were able to adsorb ions, this is schematic, to adsorb ions by stacking ions on side of a carbon pore wall. And you know, because of the size of ions, solvated ion size, you need at a time to be between 2 and 5 nanometers to maximize the charge, to minimize the volume. And people thought that below 1 nanometer, there was no way for ions to go inside pores below 1 nanometer because solvated ions were bigger than 1 nanometer. However, when we did our carbons using a very specific technique, we have shown that first, pores lower than the size of solvated ions were accessible to the ions. And second, there was a huge capacitance increase in these nanopores. So it was evidence that first, you need completely to rethink about ion adsorption into these carbons. Second, all the porous carbons people were producing were completely wrong. They need to produce carbons with very small and narrow pore size, below 1 nanometer. And then, it was also a paradigm change, new concept to prepare carbons, but also from the intellectual point of view, it was completely unexpected, and we started to work on basic understanding of everything on that. So just another example, if you move from liquid electrolyte with solvent and salt, you remove the solvent. You just take what we call ionic liquids. Ionic liquids, they are solvent-free electrolytes. You take sodium chloride, you heat at 800 Celsius degrees, you have molten sodium chloride. You can do the same with other materials, but some of them are liquid at room temperature. This is particularly the case of EMI plus cation, TFSI minus anion. So this is a liquid at room temperature. There is no solvent, no solvation shell. And you can see the size is about 0.76 nanometer, 0.79 nanometer. And when you study the capacity of our carbons in these ionic liquids, with a carbon which has a pore size of 0.72 nanometer, you have a maximum capacitance. And this was a very important message that here, when you don't use any solvent, you maximize the capacitance when the pore size is more or less equal to the ion size. So it was also a very new way of concept for preparing materials. Well, I'm going to skip that, which is modeling, and I'm going to just make a summary about supercaps. So perspective for supercaps, this is to increase energy density, which is given by half of the capacitance multiplied by square of the voltage, and to try to increase the energy density to 10, 15 watt-hour per kilogram. So you can do it first by increasing the capacitance. This is what I show you to try to understand ion size, pore size, whatever you want, to try to design new carbons with tailor-made carbons with new outstanding properties. But you can try to use also other materials which are going to mix redox reactions, but only onto the surface of materials. Fast redox reaction materials, like niobium oxide that we prepared with colleagues from UCLA. That's another way. And you try to increase the cell voltage. So there's a lot of things which are developing now with ionic liquids, solvent-free electrolytes, because you are not limited by the solvent decomposition for the electrolyte voltage window stability. And also hybrid devices. I will give you words maybe during questions, if I have questions about that, which is called the lithium ion capacitor. You take a negative electrode of lithium ion battery, graphite, and a positive electrode of capacitor, supercapacitors. So you combine energy and power. But I will end my talk by giving a few words about the French network on batteries. So this is an initiative that was pushed by CNRS and the French Ministry. We have been created in 2011. So together with Jean-Marie Tarascon, we try to develop basic science within this network on batteries. To improve the knowledge and technology transfer from research to industry, and to develop a French expertise in the field. So this is a building, 6,000 square meter. We are going to have in Amiens in December 2016. So we have three major pillars. The first one is what we call academic research center. You have 15 labs in France, including in Toulouse, obviously. We are developing basic research on batteries, any kind of batteries. Then we have Technological Transfer Center, which is led by CEA, Litten, DRT, Ineris, and IFP Énergie Nouvelle. And then we have Industrial Club. So this is two industrial are missing, but anyway. So we have companies which are partnered to the French network, and we are exchanging all together. And the dream is to design new ideas, new material, to transfer these materials to the Technological Transfer Center, and to be produced by companies. So that's the full loop. So we are working on 5 major thematics. First is advanced lithium ions. Second is capacitive storage, supercaps. Eco-compatible storage, organic materials for batteries, green batteries, whatever you want, ACV. New chemistries, lithium sulfur, sodium ion, redox flow, solid state batteries. And smart materials where we couple batteries and photovoltaic properties. We have cross-cutting research centers with safety platforms, theory platform, and a lot of in-situ techniques. And we have also something what we call pre-transfer cell. We have here in Amiens a prototyping cell. We are able to make some prototypes of batteries, and this is a safety cell, pre-transfer cell. So I would like to give 3 examples of what we did recently at the French level on batteries. The first one, advanced lithium ion, you saw that. This is the redox mechanism that Jean-Marie Tarascon at Collège de France discovered by playing not only on the cation oxidation state, but also with oxygen oxidation state. You can increase the capacity of materials. So that's really something which is in the next future, which is going to be very important. And the key issue to solve here is the stability, cyclability. You can go up to 320 milliampere per gram. You can double the capacity. On supercaps, so what we did was to try to understand the ion transfer in nanopores, and we did some in situ NMR spectra together with Claire Gray at Cambridge. And you can see here, what we did, we took a cell, we did some polarization at constant voltage here, and we have tracked the signal of anions and cations by flowing the fluorine and the phosphor signal. And you have here, during positive polarization, the number of anions and the number of cations. You polarize positively the carbon, you can see that anions enter, cations are leaving, normal. But when you go to the negative polarity, when you polarize negatively the carbon, cations are entering, normal, but anions here, constant. They don't leave. So that's something which is quite difficult to understand, but this is something which has been checked, double checked, triple checked. And we have definitely a different storage mechanism between the positive polarization and negative polarization. And this is something we have to understand deeper to try to understand how to improve again the capacitive storage in nanoporous carbons. And this is a key concern to address to design optimized structures. And the last example is about moving from lithium ion to sodium ion batteries. So this is what we did was to create a sodium-ion battery task force. You remember why sodium? The cost, drawback, 300 millivolt lower potential for sodium, so that you have a 30% energy density less, but the cost is really here the main motivation. So we started to work on this design, a positive electrode made with NVPF. This is a sodium vanadium phosphate fluorine, okay? Negative electron of carbon or antimony. And this is done in Montpellier. When you take antimony electrode, this is alloying reaction. You remember alloying reaction? Surprisingly, in sodium, it works very nicely. You have here capacity versus cycle number, 600 milliampere per gram, 250 cycles, very nice. On the positive electrode, we have designed a new material, a new structure of an old-fashioned material, NVPF. It works. This is the charge here, the discharge. Potential time. It works very nicely. And then, together with a CEA, with a technological transfer, we moved from few grams per batch of synthesis of positive active material that we did in the lab to batches. Today we are preparing 500-gram batches per batch of NVPF, and we were able at CEA to make some electrodes and to prepare the first sodium-ion prototypes in the 650 prototype, the first prototype of the world of sodium-ion batteries. And the performance were very interesting for first trials. This is 1 ampere hour prototype. This is milliampere per gram of positive electrode, very stable cycle life, very good power. 80 watt-hour per kilogram means 20% less than LFP, lithium-ion battery. Nothing optimized, very nice results. And we took a lot of patents, and we are really developing this technology, which could be, the idea would be to try to create a French filière on sodium-ion batteries. Well, and this is all the colleagues from the French network on batteries, and this is the end of my talk. Hope I have not been too long, and would like to thank you all for your attention.